Okay, in this video, we're going to talk about the concept of centering force as it applies to oscillators. And after watching this video, you should be able to use the concept of centering force to explain how it affects the period of free oscillators. Now, in class periods, we've done experiments with the inertia balance and with the mass on spring and the hovercraft and the pendulum oscillators. And we're going to use those to try to understand this idea of centering force. All right, so where did the idea of centering force come from? Well, we had noticed that the mass affected the period of the spring oscillator. The mass of the inertia balance affected its period, and the hovercraft also. But when we got to the pendulum, we noticed that increasing the mass here on the pendulum didn't affect the period. And our oscillator model therefore failed to explain one of our observations. We began trying to understand that by trying to look at how does the pendulum differ from the spring, inertia balance, and hovercraft oscillators. And there were some differences that people in class brought up. For example, some people noticed that the inertia balance, the spring, so the spring, the inertia balance, and the hovercraft all oscillated either side to side or up and down, whereas the pendulum sort of had a diagonal path, or some of you said maybe it had a curved path. So that was one difference. Another difference that was frequently brought up was sort of how it works. And some people noticed that the spring used the spring. The inertia balance had these springy side pieces, and the hovercraft, if you recall, here's the hovercraft, bounced back and forth between two rubber bands. So many people saw that as that those three oscillators used springs, whereas the pendulum used gravity to help make it move. And we focused on trying to say, well, what are we talking about here? And many of you realize that what we're kind of talking about here is the path direction, or some people use the word orientation. But a more fundamental way they differ was in this how it works. So what to call this thing about how it works? And so we created a concept called centering force as the force that caused it to work. Pendulum used gravity, the spring, these other oscillators use springs, and those are the centering forces. And I want to look in more detail about what that means. Here are some different oscillators. Let's grab the pendulum, or the inertia balance. Now with the inertia balance, when you pull it to the side, like this, these springy side pieces try to force it back that way. And then, of course, because it has inertia, it tends to keep right on moving. And eventually, it gets way over to this side. And again, these springy side pieces tend to force it back to the center. So the reason that we called it centering force is because it's a force that forces the oscillator back to the center of its oscillation. And then, of course, inertia, the tendency to keep moving, brings it back past the center, and the centering force shoots it back to the middle again. And then it shoots past there, and the centering force pushes it and forces it back to the middle. That's how it works on the inertia balance. Now let's get the inertia balance out of here. Let's look at the mass on spring. All right, so here's our mass on spring. And what we did in lab is we pulled this thing down like this. And as we pulled it down, the spring pulled up on it, forcing it to come back to the center. Now, of course, this thing oscillated up and down and up and down. But every time it got away from, here's the center right here, the center of its oscillation, the spring, that when it gets down here, the spring pulls it back. And so we said the spring was the centering force. That is, it centered the oscillator. And then, of course, it moved back and down. When it gets down here, again, the spring yanks it back to the center. So again, the spring is the centering force there. Now, let's move on and take a look at the pendulum. Now, for the pendulum, there are no springs. Instead, you have the pendulum tending to go in this direction, which is a little bit down and a little bit horizontal. Now, as we know, gravity on Earth pulls things down. This thing has to go down. So gravity has the effect of forcing it back to the center. Then, of course, its inertia brings it up like this. And as it's moving up like this, gravity grabs hold of it, slows it down, because gravity, again, is trying to force it back down. So as it rises up, gravity slows it down and then forces it back to the center. And as it goes over here, it starts to rise up because it's in motion. Gravity tries to change that motion, slowing it down. As it rises, gravity's pulling down on it, slowing down, and then speeding it up and forcing it back to the center. So in that case, gravity is the centering force. Now, the interesting thing that we noticed is that with more mass, or with more centering force, we ought to get back to the center quicker. In fact, let's go back and look at our inertia balance to examine that for a second. So, with the inertia balance, the stronger these side pieces are, the harder they can push back that way, the quicker this thing will get to the center. And then it'll go back over this way, and these really strong side pieces will slow it down really quick and force it back to the center even quicker. Now, we weren't able to change the strength of these side pieces, but if we could, then weaker side pieces wouldn't push quite as hard. And because there's some inertia there, the mass we put on there, it would take a longer time to push back. And again, if these are weaker sides, it would go like this, and these wouldn't quite slow it down as much. It wouldn't push quite as hard to slow it down and then speed it back up again toward the center. So the strength of these side pieces affects the centering force. And the more centering force, the shorter the period. Okay, this is what we'd expect is here's centering force and here's period. We'd expect greater centering force to have less period, maybe something like that, increasing or decreasing shrinking rate. Let's go back to the pendulum for a moment. Shrink that out of there. Bring the pendulum back. Now with the pendulum, we have actually two things going on. With the pendulum, you have a greater centering force. If you increase the weight here, increase the mass, you increase the weight, which is just gravity. Weight equals gravity. Okay. So if you increase the mass, you increase the weight, which increases the centering force. So this should get back to the middle quicker, and with a greater centering force, have a shorter period. But we have the conflicting fact that more mass here also gives it more inertia, and more inertia should make it go slower. So with the case of the pendulum, we had two conflicting things. A greater mass meant a greater centering force, which meant a lower period, but a greater mass also meant a greater amount of inertia, which should make a longer period. And both those things are going on. They tend to cancel each other out. All right, so again, to wrap up, the centering force is just the name we give to the force that pushes the oscillator back to the middle, then slows it's down as it's going back to the side, and then forces it back to the middle, and then slows it down to it come to a stop, and then forces it back to the middle. That's what we mean by centering force. And what we've seen, or what we suspect, is that centering force is inversely related to period. Greater centering force, lower period. Now, for those of you who are interested in a more complicated look at centering force, keep watching as we'll take a closer look at the mass on spring. Here is a look at the mass on spring. And some of you might realize or be wondering, hey, when the mass oscillates up and down like this. When the mass is down here, then the spring pulls it up like that and centers it. But you know, this has also got gravity working on it, because when it's up here, gravity pulls it back down to the center. So in some sense, the spring has two centering forces. All right? So how does that work? Well, it works just fine, and it really doesn't complicate our model at all. So let's think about what happens when we put a little bit more mass on here. Okay, we make this thing a little bit more massive. All right? So if we make that a little bit more massive, the point where it hangs without moving is actually a little lower. This spring stretches a little bit more and it hangs here. And then it oscillates down like this and up like this. But it oscillates from a center that's here and not here. All right, so what does that mean? Well, let's say, as we said we would do, let's increase the mass. So now we have a bigger mass. Well, now this spring is stretched even more. I'll redraw this over here. The spring is stretched even more, which means that when we pull it down and then let it go back up again, there should be a greater centering force, because the spring is stretched more. When the spring is stretched more, you get more centering force. That should make the period shorter, but the inertia should make the period longer, which makes you think, well, maybe the period should be the same when you change the mass. But as we know, it's not. It's very clearly more mass means more period with an increasing shrinking rate. So why is that? Well, the answer is that if you've added more mass, you've also added more gravity, which on the lower side, okay, so here's its, what we would call this equilibrium point. Down here, gravity works against the spring. So we have greater centering force from the spring, but gravity here almost acts like an anti-centering force. And because the mass is greater, we have greater gravity and greater spring force. And so we have a greater centering force and a greater anti-centering force. And so those two factors tend to cancel out, leaving the only factor that affects the period of the mass on spring being the inertia. And so, as we saw, more inertia, more resistance to changes in motion, longer period. We'll do one more quick look at this. What happens when the mass bobs from way down here to being way up here? And now the spring is very short like that. Well, again, even though the spring is very short, it's more stretched out at its very peak of its oscillation than if the mass was lighter. And therefore, now gravity is sort of the centering force, really. And if we have more mass here, then we should have greater centering force. So we ought to get back here quicker. But the spring now is sort of like the anti-centering force. The spring is pulling it upward away from the center. And again, because there's more mass here, even though the mass might bob up and down the same, let's say 4 centimeters, it's doing so with a much greater stretch spring. And so both the anti-centering force and the centering force are greater with more mass, and therefore those cancel out again, and only the inertia affects the period. And that's why when we did this experiment, we saw more mass means more period. There's 3 things going on. 2 of them cancel out, centering force and what we might call anti-centering force. Okay, that's a much more complicated look at the mass on spring oscillator, and I think for those of you who watched that, hopefully if you had questions about why the springs seem to have 2 centering forces, that explains it a little bit. If you watched it and got kind of confused, please don't be concerned about that. Really only up through the previous screen, the 10-minute mark, is all that's really important to do what we need to do for this class. If you have any more questions about centering force, please ask your teacher.